this is joint work with colleagues from SAP Security Research, Henrik, Serena, Ponta, and Hermann from the University of Dortmund and Professor Bodden. And in this talk, I want to present and discuss our case study about challenges that open source vulnerability scanners face when detecting vulnerabilities in used open source components. So I guess one thing that made it totally clear how important detecting vulnerable open source dependencies was the recent Log4Shell vulnerability that caused a lot of news and also a lot of work in the industry, and also the Equifax hack. So we clearly saw that there's a need to detect vulnerable and exploitable open source packages quickly and reliable in software systems. Obviously, this is not a new problem because there already exist multiple open source tools and also commercial tools. I guess the more well-known are, for instance, from SAP Eclipse Steady, the open source tool dependencies check from the OWASP Foundation, GitHub security alerts, and also multiple commercial tools. And the original question we had in mind and that we want to give an answer to is, how reliable are these scanners and these tools in the presence of typical development practices? So in the presence of forking, changing, and patching the open source package itself. So how well perform these scanners? And to do so, we conducted an industrial case study on projects at Develop at SAP and on Maven Central. So this boils down to three research questions. For the first question, obviously, is what are typical development practices with respect to the use of open source software packages? So how are they used? And to do so, we did a case study on 7,000 projects developed at SAP. And then we also checked how prevalent are these development practices outside of SAP to not be biased. So we checked how well and how often these identified practices occur on Maven Central. And to finally give an answer to the original question, we used a set of open source dependencies, applied the identified development practices to them, so changed the bytecode and modified them slightly, and then we compared the performance of three open source vulnerability scanners, so dependency stack, Eclipse Steady, GitHub security alerts, and also three commercial tools. So how did we identify typical development practices? As I already said, we conducted an industrial case study on more than 7,000 different projects, so ranging from microservices, libraries, actively maintained projects and projects under development. And for each of this project, we completed the complete bill of material. So this is a list of open source packages and packages each software includes. And to do so, we used the tool Eclipse Steady and the Maven Central resolution process to get all information about the included open source package. And then we classified each open source package by a unique identifier, so-called GAF, in Maven. So basically, it's the vendor, what artifact is used, and its actual versions. And we found out, similar to other studies, that the majority of open source dependencies a project includes is transitive. So this means developers do not include them directly, but they are drawn into a project through a direct dependency. And we also found out that the most of the packages any project includes, actually compile time dependencies. And in total, we found 723 different open source artifacts included in these 7,000 projects. And for these projects, we identified 249 different vulnerabilities, so-called CVEs. Furthermore, we identified that on average, a project includes 36 different open source packages. But the more interesting question was, what are the actual development practices? So we identified 4 types of practices. So first, unmodified, so open source packages are directly loaded from the Maven Central repository, so the most used one. Then we identified that people and projects include so-called patch dependencies. So in these, we had slight modified the source code, so it was a small patch applied, and also the unique identifier, the gov, changed a bit, for instance, by appending _fix to the version number. Also, we often identified so-called uberjars. So that means all dependencies were actually rebundled into a single big jar to allow easier distribution. And also we identified so-called bare uberjars. So the open source packages were bundled into a single jar, but meta information like the original names were removed. And the last type was we identified so-called repackaged uberjars. These were, again, all packages were bundled into a single jar file, and the original package names like java.com package something was actually renamed. So we identified these 4 types of modifications and development practices to actually check how prevalent are these practices outside of SAP. We checked how often we identify bare uberjars, and repackaged uberjars on the Maven Central repository. And what we did there, we took the 249 CVEs that we identified in research question 1, checked for commits fixing these CVEs, and in these commits we identified 204 different classes. And then we checked how often these fixed classes occur on Maven Central in slight modifications, so patched form, or are included in uberjars. And as a spoiler before going into the detail, we found on Maven Central all types of modifications, and most of the time we identified bare uberjars. So to give a rough estimate, so type 1 modifications we found less, and also repackaged uberjars we found less, but most of the time we found these uberjars. So for 222 of the 254 classes, we found out that they occur in uberjars or in bare uberjars, so with the metadata removed. And we not only found them in different versions of the same library, but we found them in, here it's stated as different GA. So we found that they are contained in uberjars by different vendors. So the question, obviously the original question was, what is this impact of uberjars, bare uberjars, or patched jars on the performance of vulnerability scanners? To give an answer, we, as I already said, compared the performance of multiple free and commercial tools. And how did we do that? So we took the 7 most used dependencies that we identified in our case study. And for each open source dependencies, we choose the 4 recent CVEs and use that as our ground truth. So we checked how well these scanners identify these CVEs in the 7 dependencies after applying the modifications, for instance, after merging them into an Uber jar. And what we found, surprisingly, so we found that actually none of the tools can actually deal with type 1 to type 4 modifications. And we found out that all tools, even if a single modification was present, struggle to reliably detect that the vulnerability that the vulnerability is actually present in the open source package. So here in the form of the F1 measure presented. So for unmodified, as we used as a baseline, for instance, here Eclipse Steady for unmodified dependencies detects all CVEs in all open source packages. And what we see that type UberJar and bare UberJars performs worse for all vulnerability scanners, for the commercial and the free vulnerability scanners. Also, these have been actually the modifications that we identified on Maven Central the most. So what does it mean, or what are these conclusions that we can draw from these observations? So first, we can see, and what we saw, that also C1 have here some good F1 measures. We saw in our experiments and in our evaluation that the precision was pretty low, but the recall was pretty high. So it was like they were guessing vulnerabilities that somehow relate to the open source package that they see independent of the actually used version. And what we see here for type 3, these were multiple open source packages bundled into a single jar, but with the metadata, for instance, the original names removed, that no tool, Eclipse Steady, was able to identify any vulnerabilities in such modified open source packages. And based on these observations, one could guess that these tools actually seem to heavily rely on the presence of metadata and the original name, but not actually look into the code of the open source package when trying to identify vulnerabilities. So what does it mean in summary for our original question, how reliable are these tools? So we saw in our study that the modifications are common in industrial and open source projects. And we also saw that all tools fail to cope with these modifications properly. So what does it mean? When these modifications are actually common, that means that not only the original open source artifact, for instance, log4j, is vulnerable, but also all open source projects that rebundle, repackage, or recompile the vulnerable code are actually also vulnerable. And we all saw that the lost metadata heavily decreases the tool's performance. Yeah, that's the summary. Any questions? I'm happy to take your questions.